Hi and welcome to John's Maths book. In this video, we're going to be looking at calculating the volume between two surfaces using double integration. If you like the video, then please hit the like button and I'd be delighted and honoured if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. We have two surfaces, a blue surface and a red surface. The equation of the blue surface is z equals 3 minus x squared minus y squared, and the equation of the red surface is z equals 2x squared plus 2y squared. Our task here is to find the volume encased between the two surfaces. Let's quickly take a look at the surfaces in 3 dimensions. So let's first see the red surface in isolation. And now the blue surface in isolation. And now let's take a look at what happens when we put them both together. Our first step to finding the volume between the surfaces is to find the region of intersection and then to convert this region to polar coordinates. I've marked the region of intersection on the diagram. To find where the surfaces intersect, we let one equation equal to the other. So we have 3 minus x squared minus y squared is equal to 2x squared plus 2y squared. Adding x squared plus y squared to both sides gives 3 equals 3x squared plus 3y squared. And dividing both sides by 3 leaves x squared plus y squared is equal to 1. As we can see, x squared plus y squared equals 1 is the equation of a circle with radius 1. Let's now convert this from Cartesian coordinates, so that's x, y, to polar coordinates, so r theta. So when we do this, we let x equal r cos theta and y equal r sin theta. So substituting for x, y in our equation, we have r squared multiplied by cos squared theta plus r squared multiplied by sin squared theta is equal to 1. Removing r squared, we have r squared multiplied into the bracket of cos squared theta plus sine squared theta is equal to 1. And using the trig identity, cos squared theta plus sine squared theta is equal to 1, we're left with r squared equals 1. And therefore, taking the positive root of both sides, we're left with r equals 1. To help visualize, I've sketched the region of intersection on the right-hand side of the board. As you can see, it's a circle centered at 0 with a radius of 1. Now let's look at what we need to do to find the volume. The volume is a double integral over the region R, which sums infinitesimally small pieces of area, shown here as dA. These are multiplied by a height function f of xy, and this gives infinitesimally small pieces of volume. Let's take a closer look at what happens when we sum or integrate in the r direction. When we integrate or sum in the r direction, this will represent the inner of the two integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each piece of area is the length multiplied by the width. So in this case, dr is the height and rd theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate in the r direction for this exercise, we begin at the origin of the circle, so where r equals 0. And we travel to the edge of the circle, so where r equals 1, as we saw when we converted the equation of the circle to polar coordinates. If we multiply an infinitesimally small piece of area dA by height, we get an infinitesimally small slice of volume, which is the height function shown here as f of xy multiplied by rdrdθ, which is an infinitesimally small piece of area. We can now define the limits of the inner integral. The lower limit is the origin of the circle, so where r is equal to 0. And the upper limit is where r meets the circle, so in this case where r is equal to 1. I'll deal with the height function f of xy shortly, but let's first find the limits of the outer integral. So that's when r rotates about the angle of theta. To do this, let's first visualize what happens as r rotates about theta across the region R. As r rotates, it begins at theta equal to 0 and advances 360 degrees or 2 pi radians around the circle. Each sector represents an angle of d theta. By summing each of the infinitesimally small sectors, we get our total volume, as we've multiplied the area by a height function. We do this by integrating beginning at 0 and ending at 2 pi radians. Now we understand the region when we rotate about theta, we can define the limits of integration of the outer integral. The lower limit starts at theta equals 0, and the upper limit is where theta equals 2 pi radians. Now let's deal with the height component f of xy. We have two functions between which we are calculating volume. We need to subtract one function from the other to determine the height component. To facilitate this, we need to work out which of the two is larger when x and y are 0. So which is the top function and which is the bottom function? If we now take the function z equals 3 minus x squared minus y squared and substitute 0 in for x and y, we're left with z equals 3. And the other function z equals 2x squared plus 2y squared. If we substitute 0 in for x and y, we're left with z equals 0. So in this case, our top function is z equals 3 minus x squared minus y squared, and our bottom function is z equals 2x squared plus 2y squared. We can now subtract our bottom function, 2x squared plus 2y squared, from our top function, 3 minus x squared minus y squared. And this gives us 3 minus 3x squared minus 3y squared. Converting this to polar coordinates, we substitute our cos theta for x and our sine theta for y. This gives 3 minus 3r squared cos squared theta minus 3r squared sine squared theta. If we simplify this, we have 3 minus 3r squared into the bracket of cos squared theta plus sine squared theta, and using the trig identity cos squared theta plus sine squared theta is equal to 1, we're left with 3 minus 3r squared. Now that we have our height component, we can begin to evaluate our integrals. So first we're integrating from r equals 0 to r equals 1, 3 minus 3r squared multiplied by r dr. This will give us a function of theta, which we integrate from theta equals 0 to theta equals 2 pi. So starting with the inner integral, the antiderivative of 3 minus 3r squared multiplied by r dr is 3r squared divided by 2 minus 3 times r to the power of 4 divided by 4, and we need to evaluate it between 0 and 1. So plugging in the value for 1, we get 3 divided by 2 minus 3 divided by 4, and plugging in the value of 0, we get minus 0. So this gives us a value of 3 over 4 or 3/4. And onto our outer integral, we're integrating 3/4 d theta between theta equals 0 and theta equals 2 pi. So our antiderivative is 3/4 theta, and we need to evaluate it between theta is 0 and theta is 2 pi. So when we plug 2 pi in for theta, we get 6 pi divided by 4, and that's minus what we get when we plug in the 0, which just gives us 0. So our final answer is 3 pi by 2.